This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. Today, Professor Larry Wine will tell us how his group built a mathematical model to improve our ability to catch criminals based on DNA. It's the future of forensic genealogy. There's been a revolution in our ability to measure DNA. First, we can use it for health benefits. We can understand our risk for disease and which drugs may and may not work. Second, people are really interested in how DNA tells them about their ancestry. Where did my people come from? Why am I here? That has led to the proliferation of databases of DNA measurements made by people who want to find their long-lost relatives. These databases can be used not just for ancestry, but sometimes by law enforcement to find perpetrators of crimes. It's not that the perpetrator will be in the database, that would be a direct match and easy, but sometimes their relatives might be in the database, and using relatively sophisticated algorithms, we can figure out, based on the pattern of DNA from relatives in these ancestry databases, who it might be that committed a crime. Well, Professor Larry Wine is a professor of management science at Stanford University. He uses math modeling tools to understand a whole range of problems in manufacturing, healthcare, and homeland security. He has worked on a wide range of public health issues, including HIV, anthrax, influenza, food terrorism, and biometric identification. He will tell us how he uses math modeling tools to take a long list of DNA partial matches and figure out who must be the perpetrator whose DNA was found at a crime scene. Larry, thanks so much for being here. You've recently published a really interesting paper about something called forensic genetic genealogy. What's the problem that your team was trying to address? And then we can get into what the solution is.
Okay, sure. And thanks, Russ, for having me on. I really appreciate it. So forensic genetic genealogy, or FGG, came on the scene around 4.5 years ago, hit the headlines with the Golden State Killer case. So maybe I'll just walk us through that case.
That sounds great.
You can see it. So the first step, which is typically the starting point, is that you have some bodily fluids or something you can get a DNA sample from the murderer. I'll be calling that person the target, the unknown target. And the first thing you do is compare it to the database of bad guys' DNA through the whole country, and you don't get a hit. And then you've exhausted all your other non-DNA leads, and then these cases just sit there for decades unsolved. So the new and interesting part of this...
And the reason you don't get a hit is because if this person has never been arrested or had a crime before, they won't be in the database, and you're out of luck.
Yeah, and with an awful irony, this guy happened to be an ex-cop.
Okay.
The Golden State Killer. So the next step, what's made this new is there's now these new third-party services, in particular GEDmatch and Family Tree DNA, or FTDNA. And what you do is you take some SNP data. You basically take the bodily fluids or whatever, send it to a laboratory. You get back essentially some DNA. You then send it to these companies, and this company like GEDmatch will send you back a list of like 1,000 names of people who are related to this unknown murderer, along with the centimorgan value, which is the amount of DNA that's shared between each of these 1,000 people and the target. And not only that, it gives you the names and the email addresses.
Whoa. So wait a minute. How did they get in the database? So these are not criminals, generally speaking. Is that correct?
This is like 23andMe or Ancestry.com. It's people who are doing this. The difference is that 23andMe and Ancestry.com do not allow law enforcement to use their systems, whereas GEDmatch and FTDNA do allow law enforcement.
And the reason that folks do this is simply they're curious about their ancestry and they'd like to find long lost, they're not even lost relatives, they're relatives that they never even knew that they had. And that's fun because then you can say, hey, you looks like you're my third cousin or whatever, something like that.
Exactly, right. Okay. I read something recently that genealogy is the second most popular hobby in the world behind gardening.
Okay. Oh, and actually, that's interesting because it's all about trees. But I digress. One more question about these databases is they must agree to have their name and email released as part of the deal for getting other people's names and emails.
So interesting. So at the time that they caught the Golden State Killer, that was not the case. And so there was an uproar after they caught him and it became public that these users of GEDmatch were not aware that law enforcement were using them. So as a result, GEDmatch became an opt-in system. So you had to opt in that law enforcement could use it. And as a result, it's somewhere around 30% or so, slowly climbing each year of the original users are opting in.
Okay, so good. So thank you for that distraction from me. But where we last left off is we've now they have some DNA from the perpetrator or the target, as you said, and now they have this GEDmatch. Okay, and continue about what the law enforcement does.
Right. So then at that point, you take the output from GEDmatch, the names and addresses of a whole bunch of relatives, some information about how each of these relatives are related to the murderer and how they're related to each other. And you give this to a team of genealogists. Okay. And the genealogists then try to build this family tree to figure out who is this unknown murderer. In the case of the Golden State Killer, it took a number of months. They had a few distant relatives, and they finally focused in on one person. And then the last step is to get a confirmatory sample. And they basically stalked his house. They got a sample from his car door. They went into his garbage and found a tissue. And both of them gave a perfect DNA match. And then they arrested him.
They make an arrest.
Yeah.
So a couple of things. It's possible, but not likely, that if the target has actually participated in GEDmatch or FTDNA, that they would actually be a direct hit. But that's also unlikely because you would be crazy to be a criminal who's giving your DNA out to all of these services. But it's also possible that your sibling, your first cousin, your second cousin, if it's sibling or first cousin, my guess is it's going to be easy to figure out who this is.
Right.
But my guess is that you don't always get siblings or first cousins, and it's distant relatives.
Right. So in our analysis, we looked at 17 cases from a company, DNA Doe Project, and there's great variation among the cases. So of the 17 cases, 8 of them were solved at the time they gave us the data, and some of them were easy to solve. As you say, they investigated a couple dozen matches and found the person.
Right.
In other cases, they investigated several hundred people, and the cases remain unsolved.
Okay. And this correlates roughly with whether it's a third, fifth cousin versus whether
Right.
it's a first, second cousin. Okay. So now where does your team come in?
So
sounds like a great system.
Right. So we basically are the first ones well, first I'll just say the genealogy part of the process is by far the bottleneck, certainly in terms of time. Think of how long it takes to solve a case. The great majority of it is on that. But maybe more importantly, also the chances that you solve a case can depend on how good a job or thorough a job you do on the genealogy part. And so our paper is really the first attempt to mathematically formulate the genealogy problem and then make some attempt to solve it.
And when you say genealogy, you are, I think, literally looking at birth certificates, family trees, immigration. What does it mean to do that?
Yeah. So the precise mathematical problem is, given a list of people, like let's just say 1,000 people who are related to this murder, given the centimorgan value, how much,
which is a measure of how far apart they are,
right, and then 1,000 by 1,000 matrix of centimorgan values of how these 1,000 people are related to each other. Given that, maximize the probability that we can identify the killer. Subject to a constraint on the amount of work we put in. Right. And we measure this workload by the number of people in the final family tree.
Okay. because it's not that you're building a single 1,000 person family tree. You have to make decisions about which people will be in the tree, and then build just like that sub tree. I'm trying to understand this tree building.
Yeah, you're building one huge tree, but we're making the decisions in our optimization. What's the efficient thing to do next in this tree? So I'll describe a little in broad terms. So the general genealogy problem, as posed, broadly has two stages. The first stage I would call the ascending stage, where you're starting from matches that you're going to investigate, and then you try to find their ancestors, their parents, grandparents, great-grandparents, go back in time up the tree. The second stage is a descending stage, where you finally take some of these ancestors and you're descending down looking for their descendants, their children, their grandchildren, great-grandchildren. And in the descending stage, ultimately, you're looking for a marriage between the mother's and father's side of the murderer's family tree. And once you find that marriage, assuming there's no endogamy, inbreeding, but then you know that the murderer will be some offspring, maybe not the direct child, but some descendant of this marriage.
Yes. Okay. This makes sense, and you've just referred to something that everybody knows, but that I had forgotten for a moment, which is that my mom's tree and my dad's tree are unlikely to be intermixed. So when you look at all my relatives in this database, they can. I was going to say roughly, but it's not really even roughly. They can exactly be separated into likely relatives of my mother and likely relatives of my father, and they all come together in my mother and father for me. Right. So you're trying to figure that all out.
Right.
And the miracle of mathematics allows you to do it.
Right, exactly.
So how does it work? I mean, what kind of results did you find?
Yeah, well, maybe I'll tell you a little bit more about the methods. And then,
definitely.
So first, I'll define something called most recent common ancestor. So if you and I were first cousins, we're not, but if we were, then our most recent common ancestors would be our common set of grandparents.
Yes.
That set of grandparents have parents and grandparents themselves. Those people would be common ancestors for you and me, but they wouldn't be the most recent common ancestor.
Got it.
So in our paper, we compare two strategies. The first one we call the benchmark strategy, which crudely represents how things are done in practice. And the way it's done in practice is that you're looking for common ancestors between a pair of matches. So you don't actually involve the target at all. You're just looking at these lists of matches, looking for ancestors. Then once they find common ancestors between pairs of matches, they then descend from them, looking for their offspring. What we do in contrast is we're explicitly considering the target for each of the target's ancestors. So the murderer's mother and father, the 4 grandparents, the 8 great grandparents. We're going to keep a list of possible people who are most recent common ancestors between each match and the target.
Yes.
And then what we do is calculate, given a particular list, what's the probability the true most recent common ancestor is in that list. Because, I may be the murderer, you may be the match. We find your grandparents, we're first cousins.
Yes.
But it turns out they find the wrong, we're related on our paternal side, but they find the maternal grandparents who are no relation to me.
Right. So it sounds like that first method, the traditional way, there's a lot of false leads. Like there's a lot of work that they're doing that is perfectly reasonable, but it doesn't connect to the target. Whereas your insight was, let's make this very target focused and prioritize the analysis of the people who we believe to be ancestors of the target.
Right. And so we're more efficient than the benchmark strategy on both the ascending and the descending stage. I would say on the descending stage, on the ascending stage, if you do it their way, there's the danger of either undershooting or overshooting. If you undershoot when you descend from the common ancestors, they're too closely related relative to the murder, and you don't catch the murderer. The murderer is
Right.
not in the descendants.
Right.
And you can overshoot and go back 5 generations instead of 3 generations. And then it's just very inefficient because, especially way back a couple hundred years ago, people were having 6, 7 children, and you just
So the
get
tree kind of
a huge amount to the
exploded.
tree, and a lot of it is just not very useful. On a more interesting side, on the descending side, we find that our proposed strategy is very aggressive, and it descends from these lists of potential most recent common ancestors, even when the probability it has the true most recent common ancestor is relatively small, like 30 or 40%. Whereas the traditional approach waits till you see the common ancestor, and that, 100%.
Yes.
So that's basically why our policy works well. And in terms of the actual results, again, we have 17 cases from the DNA Doe Project, which is a nonprofit. The paper's co-authored with the two co-founders of DNA Doe. We simulate each of the 17 cases 500 times, so we simulate 8,500 cases, and we find that our proposed strategy that uses the mathematics outperforms this benchmark strategy conservatively 10 times faster. So, for example, if you restrict the final family tree to have 7,500 people in it,
Yep.
which is a pretty large tree,
That's a pretty big tree.
the benchmark strategy has only solved 4% of the cases, whereas our proposed strategy has already solved 94%
Okay.
of the cases.
Now, one of the things you said as a specification early on is you wanted to minimize the work of the genealogist. So does this algorithm just run the math and get an answer, or does it have to stop at certain points and ask for some human help? Like, I don't even know what it would be, but is there a time at which it stops and says, I need an extra bit of information in order to proceed?
No, at each point in time, it's all purely algorithmic. It's basically
It's purely
said,
algorithmic.
we keep track of this huge system state that's in the order of 1 million, and we keep track of all this information. For each possible action we can take, we essentially compute kind of a benefit cost ratio, and then we make the decision whether it's investigate a particular new match or descend from a particular list of
Right.
potential most recent common ancestors without any intervention.
And so what is the typical output that you would present to law enforcement? So they gave you the sample, you went over to the database, you got your 7,000 people, you did your mathematical magic, ascending and descending appropriately. What is the output that you then hand to police force or to the interested party? And what do you tell them about that, about what you're about to hand them?
Right. So we haven't got there. I'm hoping I can come back in a year or two and give you an answer to that and say this is what. So right now, the paper simulates 8,500 cases.
Yes.
And says we can do this much faster. Now what we're trying to do is create an interface between the output from GEDmatch and our algorithms to do this in iterative fashion. So they would give us the output from GEDmatch, say, we'd get the output, we'd say, okay, first investigate match number 37.
Okay.
They would investigate it, the actual genealogist. They would tell us this is, we couldn't figure out who they were. We found.
I see. Okay. So that's when they start looking up marriage records and birth certificates and stuff.
Right. And they do that by themselves. Then they would, ideally, they would then input to our algorithm, this is how we found, we would change the system state as a result. Then we would tell them, okay, do this next. And then they would do that next.
Okay, so in a funny way, the system is learning. I'm not going to call it a mistake, but it's learning from the extra information that the genealogists learn to then come up with the next best guess and the next best guess.
Right. So it's like any decision problem over time and under uncertainty, say a driverless car, where you're keeping track of a complex system state. You make a decision in a microsecond, you get new information about the environment, you update your decision. So it's the same thing that we're doing here.
This is The Future of Everything with Russ Altman. More with Larry Wine next. Welcome back to The Future of Everything. I'm Russ Altman, and I'm talking with Professor Larry Wein from Stanford University about forensic genealogy. In the last segment, Larry told us about this mathematical algorithm that markedly improves the efficiency of analyzing a long list of potential distant relatives to figure out who is the most likely culprit and DNA match. In this segment, Larry will tell us that genealogists don't necessarily worry about losing their jobs because of his algorithm. In fact, they use some very different sources of data to contribute to the process. He'll also tell us that there are pretty thorny ethical and privacy issues that must be addressed and that his team is working on. So, Larry, I wanted to ask, are we putting people out of, is this algorithm putting people out of jobs? So you describe these genealogists who do a lot of work in order to trace these cases now. How do they respond to this new technology?
Well, I would say that genealogy is as much an art as a science. And a few of these genealogists have put in their 10,000 hours and they're expert at it. And they use some information that we don't use in our analysis, in our mathematical problems. So in particular, they use geography and occasionally they use ethnicity. So for example, one of my co-authors telling a story where all the relatives were in one state like Arizona, and then, they found one person from a family tree that was in Wisconsin. They just couldn't figure it out. Then they realized this person had been traveling for a few months in Arizona and had an extramarital affair with someone, and that was, that kind of broke the case.
Yes.
And another
Interesting.
when they had a family tree that everyone was the same ethnicity, and then they had one little spattering of Greek people from Greek origin, and then they kind of found this one person that allowed them to see the needle through the haystack. So I view our algorithm, our proposed strategy, as something that can help them when they're stuck. Because often, if they're onto some hot lead and using geography, ethnicity, whatever, but otherwise they're kind of just taking the next one off the list and just going back as many generations as they want. And this would help them decide what to do next, because these trees are huge. There's no way any person, even if they put in their 10,000 hours to, wrap their head around a tree this size.
So that's great. So they're thinking of this as a power tool that they can use among other tools to just do their job a little bit better.
Right.
Great. So the other thing I wanted to ask is, all of this genetic stuff always brings up issues of ethics, privacy. Do those issues come up in this kind of work?
Yeah, certainly when the Golden State Killer case occurred, these companies were not telling people that they allowed law enforcement. So that was a big issue. Then, GEDmatch moved to an opt-in system. But there's another aspect here that hasn't been investigated. In fact, we're in the middle of researching right now, and that's something called target testing. So what's sometimes done is, you have this huge family tree, you're in the middle of this investigation, and you're stuck. You can't find the person. But you see these people in the family tree you think might be related to the killer, but you're not sure. They're not people who use GEDmatch. These are just people in law enforcement.
So the genealogists just found these out during the course of their work, looking at baptism and marriage and whatever certificates. They said, hey, this person exists, but they're not in any of my databases.
Right. And then law enforcement literally knocks on their door and says, we're in the middle of this murder investigation. We have reason to believe you're a distant relative of the murderer. Will you give us DNA?
Whoa.
And, I gave a talk, after I gave a talk at their big conference, there's a scientific working group run by the head of FBI's forensic genetic genealogy. He invited me to give a talk at this working group, and there was a bioethicist there, and she said, this is really an invasion of privacy and unethical in her view, and there's been no study of understanding what's the benefit of this. I mean, there's some idea of the cost. So we've enlarged our model to allow this as an option to do target testing and to see how much it improves the efficiency And we don't have our results yet, but we are looking into this.
So just to be clear, the privacy that the ethicist was worried about is there's a lot of people involved here. There's the privacy of the relative who just had the door knocked on, and all they're just going about their business, and now a representative from law enforcement wants to take their DNA, and they need to know, what are you going to do with it? Is it just for this crime? Are you going to keep it forever? Right? All those issues come up.
And what if I say no?
Right. There's perhaps a less compelling issue about the privacy of the target or the potential criminal, and I think mostly we're not worried about that,
right.
For the most part. Yeah. But then there's, whenever you test the DNA of a single person, all of their first degree, second degree, third degree relatives are now also partially in the database because they all share partial DNA. So the other thing has to do with, you might not be related to the perpetrator who we're looking at now, but there might be other relatives in your family that you've just made it easier to capture, and people might have different views about how much they wanted to do that.
Right. And they will feel pressured when, a police person.
Right. And then the issues of how much this is a free choice and stuff will be. So are you looking, when you say you're working on a paper, are you looking at the ethical aspects of it, or are you looking at technical means to mitigate the ethical issues? Or both?
I view it as providing input for the ethicists and the policymakers to decide, do we need it? Because this is all the Wild West here. This is a brand new approach that's revolutionizing the solving of cold case murders.
We hear about it all the time in the news. This seems to be happening increasingly.
So I'm hoping just to shed light and to allow them to have information to make an informed decision.
So just to ask a somewhat obvious question, is it true that law enforcement is knocking on doors today, or are they waiting to hear the results of your work?
No, they are knocking on doors. In fact, I just heard anecdotally from someone who would know better than anybody else in the field. They know of a case where they knocked on 20 doors for just one case, for just one murder case.
Okay, so the doors are being knocked on, and so now we're trying to figure out what's the right way to approach this and manage it. Well, in the last couple of minutes, I wanted to ask you, you're a professor in the School of Business at Stanford. What got you interested in something so specific as forensic genetic genealogy?
Right, so I teach operations management, and I have a PhD from your School of Engineering in the old Operations Research Department that's now in Management Science and Engineering. So I view the world as an operations person. After about 7 or 8 years into my career, I kind of switched into public health and public policy issues. After the September 11th attacks, I really focused my efforts for a number of years on the catastrophic threats, nuclear, smallpox, anthrax, botulinum toxin, and I looked at the U.S. visit program of keeping terrorists out of the country using the fingerprint system at the airport. And I have a paper in Proceedings, National Academy of Sciences, and testified before a congressional committee. And that led to a switch from a 2 to a 10 finger system. So biometrics, I think, is a really interesting area, at least for someone like me. There's probability, there's statistics, there's optimization. Sometimes there's a game theory aspect. Sometimes there's an operations aspect that kind of plays to, my general training.
And they're certainly impactful in terms of societal challenges.
Right. So that led me, years later to, during the last 5 years or so, to focus on crime. So I looked at ballistic imaging. So this, instead of fingerprints, this is now you have a database of photographs of cartridge cases that come out of the gun. So it can help solve gun crimes. In my work there, it was with the Stockton Police Department, but led to the nationwide adoption of 100% processing of cartridge cases. Then I looked at papers on sexual assault kits, which again, you're looking at DNA to try to, and there's, hundreds of thousands of untested kits. And our paper was the first to do a cost benefit analysis. And we estimated that for every dollar spent on a sexual assault kit, you could save about $81 in the cost associated with a future sexual assault that's averted by testing the kit.
Yeah, and that the issue of the sexual assault seems to be very closely related to this forensic genealogy because, right, you often there will be a specific accused person, but you still need to do the DNA sequencing or the DNA genotyping. You still need to do the matching, and then you have to figure out how compelling the evidence is. Are we making progress in that area? Because we've heard about this in the news every now and then about, as you said, thousands and thousands of unprocessed kits. It seems like a real justice issue here.
Yeah, and there's a lot of money being thrown at it. Like anything else, more money could be thrown at it, and the national backlog could be processed quicker. But there certainly has been steady progress.
Good. Thanks to Larry Wine. That was the future of forensic genealogy. You have been listening to The Future of Everything with Russ Altman. You can follow me on Twitter at RBAltman, and you can follow Stanford Engineering at StanfordENG.